Before starting the topic, let me ask a question to Julie and Lily. That I have two plates. One is a thick plate and the other is a thin plate. Both have equal sized notch, equal sized flaw or a crack in them. Now I want to use them for application. I'm confused which plate will sustain for a longer time, which will not fracture prior, and which plate out of them will fracture prior. The presence of notch in which plate will be more dangerous. I asked Julie and Lily about it. Julie said thick plate will be more dangerous if you use them for application. Lily said no, it's the thin plate which will fracture prior if you use them for application. I asked the reason for a thick plate being more dangerous to Julie, and she said for that you have to understand a few concepts, and that concept which Julie is telling we will study now. In our previous video we have seen that Irwin proposed an equation that is failure strength equal to critical strain energy release rate multiplied by Young's modulus divided by pi multiplied by crack length to the power half. Here GC is critical strain energy release rate, that is strain energy released divided by per unit crack area. So A is the crack length and B is the crack thickness or the specimen thickness. So now Irwin later realized that he can modify this equation by replacing root of GCE with KC. KC is critical stress intensity factor or fracture toughness. He modified this equation and wrote a new equation, sigma f equal to Kc divided by root pi a, which we can write as Kc equal to sigma f root pi a. If we don't want to write in critical terms, that is we can write K equal to sigma root pi a. When the applied stress reaches the failure strength, the stress intensity factor reaches the critical stress intensity factor or the fracture toughness. In that case, failure will occur in the specimen. Now, please note K is stress intensity factor. Now, what is stress intensity factor? It's a factor that describe intensity of stress at crack tip. So if this is the stress, this is the flaw or the crack in a body, and when we apply load on it, in that case the stress lines, they will get concentrated at the crack tip. Here we can observe that at the crack tip the stress lines or the flow lines get concentrated, by which the stress at the crack tip get amplified, and we can draw the stress at the crack tip will be sigma m and the stress at the edge will be sigma. So if we draw it, we can draw it in this manner, where at the crack tip sigma m is the stress value, and we can observe that there is uniform separation in the flow lines near the edge. So here the stress will be sigma, Now Inglis has given an equation for sigma m. He determined the stress distribution and suggested that sigma m is equal to 1 plus 2a by b times sigma. And if the crack is, here please note 2a is the minor axis of the elliptical crack and 2b is the minor axis and 2a is the major axis of the elliptical crack. So if the elliptical crack is very thin such that the crack length is 2a and the radius of curvature is rho. Rho is b square by a. In that case, the maximum stress will be 1 plus 2 root of a by rho multiplied by sigma, because we know that rho is very less than a. This because it's a thin crack, so in that case rho will be very less. So we can write sigma m is equal to 2 root of a by rho multiplied by sigma. And if you want to see stress concentration factor, that will be equal to sigma m by sigma, and that will be equal to 1 plus 2a by b, or it is equal to 2 root of a by rho. So this is stress concentration factor. We should note that all these terms are different. It's a stress concentration factor and that was stress intensity factor, and if it reaches Kc, that is critical stress intensity factor, which is also called fracture toughness. Now if we see the equation of stress intensity factor in more general way, we can write in general K is equal to, or Kc is equal to y sigma f root pi a. Here y is a constant, geometric constant, that depends on crack and specimen geometry, and it also depends on the load application and the manner in which load is applied. Now let's see how Kc depends on how fracture toughness depends on crack geometry. If it's a center cracked specimen where the crack is through the thickness and the plate is infinite, the width of the plate is infinite, in that case the fracture toughness, as I mentioned, it's Kc equal to y sigma f root pi a. Y is some function of a by w. A is the crack length, w is the width of the specimen. So if it's a center cracked specimen in a infinite width plate, in that case y is equal to 1, and if it's a edge crack in a semi-infinite width plate, in that case y is nearly equal to 1.1. Likewise, there are several mathematical complex equations that are present for single edge cracked specimen, double edge cracked specimen. So there are multiple such equations. For that we can refer fracture mechanics books. Now let's see the dependence on specimen geometry. It was there already, but this is a specific case which we are discussing earlier. Here this is a thin plate and this is a thick plate. What is the difference between the two? The plastic zone that is formed ahead of the crack tip, because it's an elastic plastic material. The plastic zone that is formed ahead of the crack tip, it will cover throughout the thickness. However, the plastic zone that is formed in the thick plate, this will only be at the center of the plate. It will not be able to cover throughout the thickness. So because the plastic zone is present throughout the thickness, the plasticity has initiated throughout the thickness. And because plasticity has initiated, the material will undergo deformation, plastic deformation. And during that process, there is elongation in length and decrease in cross-sectional area. That is, the material undergoes necking. If this is x-axis, this is y-axis, this is the z-axis. In this case, there is strain in z direction. However, because the plastic zone is only at the center, there will be no strain in z direction. In this case, the material will undergo brittle failure in this case. However, the material undergo ductile failure in this case. In order to break a thin specimen, high energy has to be applied. However, in order to break a thick specimen with a lower energy, the material undergoes failure. There is no strain in z direction, and that's the reason this situation is called plane strain. And there is stresses is triaxial. Stresses that are present in the material is in all the three axes, but no strain in z direction. And this scenario is called plane strain, plane stress, where strain is present in all the three directions, but stress is not present in the third direction. Now when you draw, because we have to apply a higher energy to break a thin specimen, so this specimen will sustain for a longer time. However, if you want to use a thick specimen, it will have lower fracture toughness. This material will break very early, very soon. In that case, a thicker specimen will be more dangerous. Now, Julie wins. What she said is a thin specimen will sustain for a longer time, a thick specimen will be dangerous. Now, if you plot the fracture toughness with thickness of the specimen, we know when thickness of the specimen is very less, in that case we have to apply very high energy to break the specimen. The fracture toughness will be very high. However, if thickness of the specimen is very high, we have to apply a very low energy to break the specimen. The fracture toughness will be very low in that case. Now, if you plot it, it comes like this. Now, just after reaching some thickness, if you keep on increasing the thickness of the specimen, this material will always undergo a brittle failure, no matter this small amount of plastic zone will not affect it. It will always be small. If you keep on increasing the thickness, this plastic zone will have no effect. The material undergoes brittle failure in that case. So as I mentioned, this is the plane strain condition where the material undergo brittle failure. However, this is the plane stress condition. We have earlier seen that K is equal to root of GCE. So if you want to write, you can write K square equal to GE in plane stress condition, and in plane strain you can write K square equal to GE divided by 1 minus nu square. And here the material undergo flat fracture. However, in this case, in the plane stress condition, the material undergo ductile fracture with shear lips present on the fracture surface. So there is always a thickness. There is the formula that is given for a thickness, that is 2.5 K1C sigma y to the power square. So if the specimen exceed this thickness, in that case the material undergo plane strain failure. However, if the specimen is having lower thickness than this, in that case the material undergo plane stress failure. Generally, plane strain fracture toughness is determined because it will not depend on thickness from now on. Just after reaching this thickness, the specimen won't depend on thickness. So this is determined, plane strain fracture toughness is determined. Now, after the dependence on crack and specimen geometry, let's see how it depends on load application, load direction, dependence on load direction, loading direction. So for understanding this, I suggest you to take a 2 rectangular box or 2 dusters in your hand. Now let's see if this is one duster and the other duster is at the bottom of this. You keep one duster on the top of the other. Now you apply tensile load so that the 2 dusters start opening. And in the second case, you provide a shear force, in plane shear, such that this particular duster will go inside and the second duster will go outside. And in the third case, you provide some kind of rotation out of plane shear. Now you apply shear stress in this direction. So the first case, that is called mode 1 loading, where you apply, if this is the crack in the specimen, you are applying load in this direction such that the crack opens up. So here you are applying tensile load on the crack surface, on the fracture surface, such that the crack opens up. And in the second case, if you assume these are the 2 fracture surfaces and this is the leading edge which connects the 2 fracture surfaces, in that case what you are doing, you are applying a shear stress, in plane shear. You are applying a shear stress such that this part goes inside and this part goes outside. Assume these are the 2 dusters, so that if you apply a shear stress, this will go inside and this will go outside. So this is the mode 2 loading. And in mode 3 loading, what happens? you start rotating this. If this is the first part, you apply a load in this direction and this you take out. So in mode 2 loading condition, if this is the leading edge, your shear stress that is applied, it is normal to the leading edge. However, in case of mode 3 loading condition, shear stress that is applied, it's parallel to the leading edge. So it is parallel in case of third mode loading condition, mode 3 loading condition. So leading edge, your shear stress that is applied, it's parallel to the leading edge. You can take an example of tearing of paper. In that case, you are applying mode 3 loading condition. In most of the conditions, there is crack opening. So mode 1 fracture toughness is mostly determined.